Okay, hello everyone. I'm Thomas Peron from University of São Paulo. Thank you, the organizers, for inviting me to this webinar on spectral methods. This presentation will be about the spectra of random networks in the weak clustering regime. This is actually a joint work with Pang Ji from Fudan University in Shanghai, Jürgen Kurz from Humboldt University in Berlin, and Francisco Rodrigues, also from University of São Paulo. So let's start with some motivation. One of the great mottos in network science is the study of the relation between topology and dynamics. And in papers addressing dynamical process in networks, it's quite common to read sentences like this. We want to study the relation between topology and dynamics, and we hope that these results help us to understand the dynamics of real-world networks. However, if we take a network generated by a random network model, and if we do a zoom in its topology, we'll see a local structure more or less like this, so something that resembles a tree. On the other hand, if we take a real-world network, we'll do the same, analyze the local topology, we will probably see something much very different. We'll see the occurrence of triangles or other types of subgraphs, besides degree-degree correlation, modular structure, and so on. So it is known that real-world networks have much more rich structure. So then we kind of notice that there is a gap between what we are studying with random models and what we are trying to model in real networks, because essentially the local topology of these two types of networks can be quite different. So then in this presentation we'll pose the following question: what are the effects on network dynamics of the simplest subgraph that we find in real networks, but it is absent in random models? Or, in other words, what are the effects of triangles in network dynamics? But you might ask yourself that this is probably already an extensively studied topic. Yes, indeed, there are many other there are many contributions that already addressed the effects of clustering and network dynamics. Here I'll mention just a few. For instance, in the context of synchronization of phase oscillators, McGraw and Menziger dedicated a series of papers to this problem. Here I'm showing an example from this paper, PRE from 2007. And here in this paper, the authors studied Cruel multiple model on clustering networks, or in other words, networks that have a significant number of triangles. And what they found, one of their results is the following. Here I'm showing the other parameter as a function of the coupling strength between the oscillators, or how strong they feel each other. And they verify that when the networks have high clustering, and by the way, by high clustering here, clustering, I'm just by using the word clustering, I mean the tendency of groups of three nodes to form a triangle. So when I say high clustering, it means that the network has a high number of triangles. So in this scenario, we have one type of dynamical behavior here, one phase transition, but then when the clustering is low, we observe a different synchronous dynamics. So in this case, we can say that the clustering is affecting the network dynamics. Also, one example coming from percolation. Here I show one result by Newman, 2009. Here Newman's investigating the size of the gyre component S as a function of the probability, or the occupation probability phi. Here, when the clustering coefficient is equal to 0, and clustering coefficient is a measure that quantifies the level of triangles we have in our network. When is equal to 0, we have a locally tree-like network that does not have triangles. So then when c equals to 0, we have one signature here. But then when the clustering is increased, or when the number of triangles is increased, we have a different a different behavior. So then again here we can say that the number of triangles is influencing the network dynamics. However, we have also results that point to a different conclusion regarding the role of triangles in network dynamics. For example, here I show one contribution by us on PRE 2013. That we were also analyzing the effects of triangles on the synchronization of Peron-Moto oscillators. And it turns out that when comparing networks with different levels of clustering, we actually didn't observe significant differences in the phase transitions of these networks, in apparent contradiction with the early results by McLaughlin and Menzinger. But of course, the networks used in these cases are different. The models used are different. But then we'll clarify this point later. And there are many other people that investigated the influence of clustering on network dynamics. I'll highlight here one contribution by Melnick, appeared in 2011. The authors here verified that actually mean field theories, initially designed for networks that do not have clustering, these mean field theories, they in some situations they might work in describing the dynamics of clustered networks, more or less in line with our findings in 2013. Also, Ejero, in this PRE in 2011, when investigating the Ising model on clustered scale-free networks, verified that as the number of triangles is changed, the critical temperature of the phase transition does not change. So also more or less in the same pointing to the same conclusion that clustering does not affect this particular dynamical property. And also there are more people that investigated the influence of clustering network dynamics. Here I'm mentioning just a few. So then now we want to clarify this point. Does clustering or triangles affect network dynamics? So to answer this question, we will analyze how the spectra of networks is changed as we vary the number of triangles. And one general way to investigate how a particular network feature impacts on dynamics is to analyze the network spectra, because at the end many dynamical properties, critical points in phase transitions, at the end they depend on the eigenvalues of the adjacency matrix or the Laplacian matrix. So we'll focus here in this work on the cluster random network model independently proposed by Newman-Miller. And but before we explain this model, let's just briefly recall how it is the traditional configuration model. And this the traditional configuration model, we initially set a degree distribution from which we derive a degree sequence, and in this degree sequence each element states how many edges each node will have, and then by randomly selecting each node, each edge, we can match these stubs and we construct our network. And in this model one can show that the transitivity or clustering coefficient will be given by this, and the transitivity will measure how many triangles will quantify how many triangles our network have when t equals to 0. As I said before, we have a tree network, a locally tree-like network, but as this quantity grows, then the number of triangles in our network increases. In principle, this quantity can be different than 0, but then we see that we have a factor here that depends on the number of oscillators. So the larger our network, the less triangles we have in its topology. So of course this model is not a good model to investigate the influence of triangles in network dynamics, for instance. But then we'll turn to the so-called Newman-Miller model. Here in this model we initially set a joint degree distribution from which we derive two degree sequences. In the first degree sequence each element will say how many single edges each node will have, and by single edge I mean edges that do not participate in triangles. And we'll also have another degree sequence saying how many triangles each node will have. So then by randomly matching these edges and triangles, we construct our clustered network. And here is important to mention that this model, why we say that we have networks in the weak clustering regime, this is because this model does not generate overlapping triangles. So a triangle will never share an edge with another triangle. And this sets an upper bound for the transitivity, this coefficient. So then we say that we are in the weak clustering regime. And we can show that the transitivity in this model is given by this quantity, and notice that we do not have anymore a term dependent on n. So in the limit of the thermodynamic limit, this quantity will be non-zero, will be non-vanishing. Okay, but actually we will not use precisely the traditional configuration model. We will actually use the expected degree configuration model, because actually the traditional one has a minor inconvenience that we'll discuss now. So the traditional configuration model, we have a degree distribution from which we derive a degree sequence, and if we generate an ensemble of networks, we can calculate the expected number of edges between nodes i and j, and this will be given by this quantity. But the minor inconvenience I mentioned is the following. When it turns out that the edges are not statistically independent. When we are in the process of generating the network, matching these stubs, when we connect, for example, nodes i and j, the node j, it will become less likely that this node connects to other nodes, and this is simply due to the fact that its degree has been decreased. So then its chances to connect to other nodes consequently is also decreased. Then this may induce some correlations in our model, which in turn will make the analytical treatment more tricky. And then we want to avoid these complications, and then for this we'll turn to the so-called expected degree configuration model. In this here we define the probability of connecting nodes i and j is this quantity. Here now we are defining a priori the probability of connecting two nodes by this quantity. Before, in the traditional configuration model, this probability arises as a consequence of the connection process, but now here we are defining this probability to be as this. And then our previous our degree sequence now becomes the expected degree sequence, because when we generate an ensemble of networks, the actual degree of the node will be narrowly peaked around the K1, for example, around K2, and so on. So then these quantities become the expected degree of each node. And just to mention an example, the traditional Erdős-Rényi random network is recovered in this expected degree configuration model when the degree sequence is all the elements of the expected degree sequence are the same. So and pk here I will be mentioning the expected degree distribution from now on. So to see more details about this model, you can check Shungen Lu PNAS 2002. But we wanna investigate the effects of triangles. So then we'll use the expected degree configuration model for single edges and triangles. In this model, we'll define that the probability of connecting two nodes via single edge is given by this quantity, just as similar as before for the traditional model. But now we have also defined a probability of connecting a triple in a fully connected subgraph or in a triangle, and we'll do so by defining that the probability of connecting these three nodes to be as this, and it will depend on how many triangles, it will depend on the expected degree of triangles that from each node. And one can show that the structural and dynamical properties of both models, of the expected degree configuration model of triangles and the normal configuration model for single adjacent triangles, the properties of the structure properties and dynamical properties of these two models, they will, in the limit of large networks and large connectivity, they will converge. They will become the same. Okay, so our goal is to calculate the spectral density lambda of the adjacency matrix, and here I'm calling the eigenvalues of the adjacency matrix as lambda. And in order to do this, we will follow the strategy of proposed here in this paper by Nadakuditi and Newman, which is first we'll calculate the spectrum of the modularity matrix B, defining as this. It is the adjacency matrix A minus its ensemble average, and these two matrices have the following properties. Well, the ensemble average of the adjacency matrix is defined to be as this, as in the expected degree configuration model. Here I'm mentioning the properties in the traditional expected degree configuration model. And since these elements are Poisson distributed, the variances of the elements of the adjacency matrix, they will be just the same. And by definition, the average element of the modularity matrix will be equal to 0, and its variance will coincide with the variance of the adjacency matrix. And now the whole problem of calculating the spectral density of the modularity matrix is reduced to the problem of calculating the Stieltjes transform of B, which is given by this equation. And this in turn is will be reduced to the problem of calculating the so-called average resolvement. So how can we do this? So as I said, our goal is to calculate now the average resolvement of the matrix B, and to calculate it, we will try to find a self-consistent relation for this quantity. And to find such a relation, let's consider a random symmetric matrix X, a generic matrix X, and we'll partition this matrix in the following way. We'll define here a big block Xn, and here the last column will define as An, and its transpose also here, and X and N is just the last element on the diagonal of matrix X. By partitioning the matrix as this, we can come up with two self-consistent relations. One self-consistent relation is for the elements on the diagonal of the inverse of matrix X, because we want to calculate this average resolvement, so we need to find some way to calculate the inverse of the matrix X. And we can find another self-consistent relation to the off diagonal elements. And besides this, in the limit of large degrees, we can just approximate the average element on the diagonal of the inverse matrix as the following expression. Here we are assuming that these elements in this expression, in the limit of large degrees, they will be narrowly peaked around their average, so we can write this relation as this. So now the whole problem in calculating the average resolvement is how to evaluate this sum here. And we can open the sum as this. First, the first element is the summation when j equals to k. So we have this first element, and we are also assuming that the elements of the inverse of matrix X are independent are not correlated with the elements of the vector A. And we have the second element for the summation over the terms of j when j is different from k. And then to calculate the first term is It's quite straightforward. We just need to notice that matrix X is lambda identity minus matrix B, and the elements, it turns out that the elements of vector A are just given by minus the elements of the modularity matrix. And A squared will just be given by the variance of the adjacent matrix. And then, as we mentioned before, the variance of the adjacent matrix will be equal to the average element of the adjacent matrix, which this element will contain information of the probability of two nodes being connected in this configuration model. Here the probability two nodes can be connected in this model of single adjacent triangles. Two nodes can be connected either via single edge or via triangle. So this is the information that is contained here. So then we are left how we need to calculate this second term, and this can be done through this second relation, through the second self-consistent relation. We just need to insert this term here, and then again we can assume that the elements of the inverse of matrix X are independent from the elements of vector A. And then to calculate this term, we need to notice that this term actually measures the probability of finding subgraphs of four nodes in our configuration model. But in other words, it is measuring the probability of finding subgraphs that follow this pattern. But actually, our configuration model only generates two types of subgraphs: single edges and non-overlapping triangles. Actually, this type of structure can appear, but only as a side effect of the connection process. So in the thermodynamic limit, this type of subgraph tends to vanish. And then it turns out that the only non-zero terms in this sum will be when m equals to n. So then, and when it equals to n, we'll have that this term will be proportional to this average, which is just the probability of connecting the three nodes in our model. And as it is just as defined previously, this quantity will be proportional to the expected degree of triangles of the three nodes. Okay, so now we have all we need for our equations. Just we can rewrite this last term as this, just replacing all the terms. We have now this bigger equation, and now it is convenient to relabel everything to just make more easier the analysis, and then we can define a function gamma that will depend on number of single edges in triangle as this. So the function gamma will be given by this first equation, where hs is given by this equation. Then we have the function ht, and the trace of the average resolvement we can rewrite also in terms of function gamma. And finally, we get the spectral density by calculating the imaginary part of function g. Okay, so but before we start calculating the spectra of networks that have clustering, it is convenient to first see if our equations reduce to a well-known case, just to be safe. And then let's check a case that we know well. It is, for example, the traditional random graph, the ER network. In this case, we have the average number of triangles equals to 0, and translating this model in the ER network in the expected degree configuration model, we only have single edges, and the distribution of the expected degree of single edges will be given by this, will be given by just a delta. Then the function gamma is reduced to this one, to this first equation, and function s will have two solutions, and we'll choose the one that leads to a positive density. And by doing the calculation, we get that we recover the spectral density given by the semicircle law. So it works in this case. But now let's see how our equations perform when evaluating the spectra of networks that have single edges and triangles. In principle, we can just take the generalization of the ER network for in this model when we have single edges and triangles. We can in principle set a joint degree distribution given by a double Poisson. And this is as before, this is translated in the expected degree configuration model as double delta distribution. However, we before we analyzed one case when we don't have triangles, but now we want to see the other extreme case when we only have triangles. In this case, the average number of single edges is equal to 0, and then our equations are reduced to these three here. So here the main problem is to solve this polynomial to find the solutions for function ht. Ht will be a complex valued function, and then after having the solution for ht, we can substitute in function g and then get the spectral density rho lambda as before. So now we have so far we made a series of approximations. We derived a set of equations to describe the spectra of networks. Then, since we did some approximations, we need to check with numerical experiments. So let's check. So now here an example of a random network with only triangles in this model. And the blue line depicts the theoretical analytical solution obtained by solving these three equations, and the gray bars are the histogram obtained by numerically diagonalizing the matrices. And we see that it agrees. They agree very well. And here the red dashed curve. It is the semicircle law for traditional random graphs. For a random graph that has the same connectivity, the same average degree as the clustering networks that we studied here. So just to serve as a reference for us. So we see that they are indeed different. When we have triangles, the distribution tends to be more skewed. And here on the right, I mark the position of the largest eigenvalue of the adjacency matrix. And actually, it is this quantity that is more important for dynamical process in networks. So many critical points, many critical properties like the critical coupling for the onset of synchronization in phase oscillators, the epidemic thresholds in disease dynamics, they depend on the one can express them as a function of the largest eigenvalue of the adjacency matrix. So then we should know how to evaluate this quantity, and I haven't mentioned so far how we can do this. So let's check. So what about the largest eigenvalue of the adjacency matrix? So far, as remember, as I explained in the beginning of this presentation, so far we found the eigenvalues of the modularity matrix B. But as I said before, we can obtain the eigenvalues of the matrix A in terms of the eigenvalues of matrix B. So just rewriting the adjacency matrix as this, we can calculate its eigenvalues through the eigenvalue equation here, but then we can rewrite it as here. Now here we have the resolvement that we already calculated and the ensemble average. And then to get the largest eigenvalue, we need to solve this equation together with the condition that the spectral density is equal to 0, because, well, the largest eigenvalue does not belong to the bulk. Okay, so for the extreme case when we have the average of single edges equal to 0, Our ensemble matrix in our random network will be given just by this, where T is the vector with containing the average, the expected degrees due to triangles. Substituting this, the ensemble average here, we get the following relation. And by the way, just we should relabel the eigenvalues of P as Bi and its eigenvectors as Xi. By doing this, we get this relation. And from the solutions of this equation will give us the eigenvalues lambda. For example, here 1, the constant 1, here it is this horizontal dashed line, and the blue lines are the solutions of the left side of the equation. When the two curves intercept, then we have the solutions for the eigenvalues. And from this graphical solution, we see that the eigenvalues of the adjacence matrix and the modularity matrix, they are interlaced. So the eigenvalues of the adjacence matrix will always be upper bounded by the eigenvalues of the modularity matrix, apart from the largest eigenvalue, lambda 1, which can grow indefinitely. So let's now see how can we calculate how the largest eigenvalue for the clustered random graph looks like. We just need to solve these two equations together, and in the extreme case, when the average number of single edges is equal to 0, we can get this simple expression, and this is what we mark here. And notice that the largest eigenvalue of so to speak Erdős-Renyi clustered random graph looks like this. We have a term proportional to 2 times the average number of triangles plus 1, plus a third term 1 over 2 times the average number of triangles. So here we have the blue line is this theoretical solution. There is a gray line behind it showing the result from the numerical calculation. So they match very well. But then since we now have an expression for the largest eigenvalue of clustering networks, let's compare with the largest eigenvalue of traditional random networks. So this is the here on the right, it is the largest eigenvalue of traditional ER networks, which is given just by the average degree plus 1. So when we compare with the analogous result for the clustering network, we see that we have something that is the average degree plus 1, but we have an additional term proportional to 1 over the average degree. So since we know that many dynamical critical points in network dynamics are proportional to 1 lambda 1, so since the two expressions are different, we expect to see some differences in the dynamics. So let's analyze some previous results in the literature in the light of this result we just uncovered. So first, in the percolation example I initially showed in the presentation, in this particular example, Newman, the author, has used networks with average degree equals to 2. So in this case, this third term will be significant in comparison to the other ones, and then since this term will be significant, we expect that the difference between the between clustered and non-clustered networks will be significant. So indeed, when we have clustering equals to 0, we have this curve, and when the clustering coefficient is larger, we have another percolation threshold. So it makes sense when analyzed in the light of this, in the light of our result. Another interesting result here by Hackett et al. In this result, in this paper, the authors are analyzing the cascading failures, and here I show the size of the cascading failure as a function of occupation probability of the sites. And then here, just to clarify the notation, Z, it is the average degree, and F is a parameter that when F equals to 0, we have no triangles in our network, and when F equals to 1, we have the maximum possible triangles allowed for this model. And then here, for when the average degree equals to 3, we have these two transitions where we see that the critical points are clearly different. But then when the average degree is increased to 5, we see that the difference between the thresholds it gets smaller. So it makes sense with our result, as we expect that as we increase the average degree, we expect this term will be smaller and smaller, and then the difference between cluster and cluster networks will be smaller. And then, as of our previous result from some years ago, when we were investigating the synchronization dynamics of clustering networks, in this particular example, we used an average degree equals to 20. So this term will be almost negligible in comparison with the others. So then, in this case, we don't expect to observe significant differences between the dynamics of clustered and non-clustered networks. Indeed. So here, when we this is why we didn't see any significant difference. So because the average degree was set in a way that this term will be negligible in comparison to the others. So it makes sense with our estimation. So finally, a last example. Let's see how the our equations perform when we have a more complicated expected degree distribution. So in this case, we have an expected degree distribution given by 2 delta when P1 with probability P1, our nodes will have expected degree equals to T1 and T2 otherwise with probability P2. In this case, the calculation of the function h becomes a bit more complicated. The polynomial gets a bit more complicated, but still we can solve it. And by solving it together with function g, we can insert the solution in function g as before, and we get the spectral density rho lambda. So then, by solving the equations, we get we can again compare with simulations, and we see that the blue line agrees very well with the results obtained from directly diagonalizing the matrices. And then notice that again the distribution is skewed. And regarding the largest eigenvalue, we can again use the relation we found before, and by doing a first order approximation, we get an expression for the largest eigenvalue proportional to the moments of the expected degree distribution. And it turns out that this in first order approximation, the largest eigenvalue of clustering networks becomes identical to the result by Chung and co-workers for the traditional expected degree configuration model. And here I compare this theoretical solution with the numerical result. Here the agreement is not good as before for the ER cluster network, but still the estimation is not that bad. Okay, so summarizing, summing up what we did. So in this presentation, we extended the approach by Nanda-Kuditi-Newman to networks that have a non-overlapping number of that have non-overlapping triangles. The approach proposed by then is designed for the traditional expected degree configuration model. We we extended how this is done when we have another type of subgraph, and we saw that the results reproduce quite accurately actually the skewed distribution of clustering networks. And when we calculate the largest eigenvalue of clustering networks, we saw that there is a vanishing difference between the largest eigenvalue that we find for clustering networks and the respective value in non-clustering networks. And this explains why we have different conclusions in the literature regarding the dynamics of clustering networks. It depends on the difference between the dynamics of when we have triangles and when we don't have triangles. This difference will depend on the average degree. And then we can also think about generalizations for the method we developed here. One can think about generalizing for other types of subgraphs. For example, we can include correlations in our random matrix that contemplate the existence of 4-node subgraph as this or other clicks. But then, of course, the equations get more difficult to solve. So then about the question that we initially posed in this presentation, do triangles affect network dynamics? And the answer is, well, it depends. At least in the weak clustering regime, we can say that triangles will matter only when we have low average degrees. Okay, so if you want to see more details about the work, you can check our paper. And thank you very much for watching until this point. If you have any questions, I will be happy to answer them.